On 3 separate missions, a crew was launched into orbit to dock with the orbiting Skylab and to occupy this 100-ton spacecraft for 1 to 3 months. I was the scientist pilot on the second manned mission, and my name is Owen Garriott. This is the wardroom of our Skylab simulator, a nearly exact replica of the real spacecraft, which is still in an almost circular orbit around the Earth. The main purposes of the Skylab missions were to show that human beings could live and work effectively in space for extended periods of time, to conduct experiments in basic and applied science, and in weightless conditions above the Earth's atmosphere. We also took thousands of photographs of the Earth to survey its resources and studied the sun in order to better understand its variable and highly dynamic behavior. In general, we found it pretty easy to adapt to living and working in this weightless environment. But we did have a few adjustments to make. We also took advantage of our weightless or zero-G condition to demonstrate some of the basic laws of nature for science students in ways that were difficult or impossible to duplicate here on Earth. I think we marvel at phenomena like these, partly because they just plain look strange, and partly because they remind us that we take for granted the force of gravity and the existence of inertia. We may also be amazed by the fact that a feather and a hammer are accelerated at the same rate by the gravity of the moon. Since the moon has no atmosphere to slow them down, they hit at the same time. We tend to forget the importance of Newton's realization that any 2 objects attract each other, that gravitation is a universal principle, not confined to the Earth. In other films of this series, we will explore the many phenomena in zero-G and use some of them to illustrate some of the basic laws of nature. Now, I'd like to start examining the phenomenon of zero-G itself by asking a simple question. Why did I feel weightless up in Skylab? Some people might answer that Skylab was so high as to be beyond the Earth's gravitational pull. This answer is quite wrong. At an average orbital height of 435 kilometers, we were only a few percent further from the center of the Earth than you are today. The gravitational force pulling us toward the Earth's center was only about 12% less than it would have been on the ground. Most of the time, the force of gravity was the only significant external force acting on us. Why then do we use the term zero-G? To understand why, let us examine the motion of a satellite. The little cannon will serve to simplify our explanation, just as it did for Sir Isaac Newton when he first announced the laws of gravitation and motion. If the cannon is fired in the vacuum of space and is also free from the gravitational pull of another body, the cannonball, in compliance with Newton's first law of motion, would travel in a straight line forever at a constant speed. Now, when we introduce a small planet, another of Newton's laws, that of universal gravitation, comes into play. This time, the cannonball, under the influence of gravity, will fall back to the surface of the planet. If we increase the powder charge and fire the cannonball at a greater speed, it may even travel most of the distance around the planet before gravity pulls it back to the surface. Now, if the initial velocity is made precisely correct, the gravitational acceleration toward the center of the planet will produce a curved trajectory which exactly matches the curvature of the planet's surface. The cannonball is now in orbit. The same holds true for orbiting space vehicles, which usually follow an elliptical path around a planet. As with the cannonball, a planetary orbit is the result of a balance of forces: gravity, constantly accelerating the satellite toward the planet's center, and inertia, the tendency of a satellite to move in a straight line. We may say the satellite and everything in it are continually falling together, since they are merely responding to the force of gravity. Since gravity accelerates satellite astronauts and assorted baggage equally, they have no noticeable acceleration toward or away from each other. Unless some non-gravitational force is acting, such as a muscular push or pull, everything inside a spacecraft remains at relative rest. This explains what you see in orbit. Or for another example, in the Apollo spacecraft coasting toward the moon. Again, gravitation is the only force acting. At a certain point on the way to the moon, the gravitational force of the Earth and the moon nearly balance each other. The crewmen felt no different at this special point because they were always in free fall for the entire trip. As long as gravitation is not opposed by any other force in space, you feel weightless. The sensation we call weight is caused by the pressure of uneven support, by gravity being opposed by the upward force of a chair or the floor. The feeling of weightlessness is similar to what you feel underwater, where your body is evenly supported. But there are important differences because even in neutral buoyancy, you still have many ways to distinguish up and down. In orbit, these minnows could not orient themselves and frequently swam in tight loops during their entire lifetime in Skylab, which was about a month. Even though they had spent their whole life in the water, weightlessness was a new sensation for them, and they responded in this very unusual manner. The weightlessness of orbit can be exactly duplicated for almost 30 seconds if the vertical flight path of the aircraft follows a parabolic arc. So 0G means the absence of support forces. It means free fall, a spacecraft following an unconstrained track through space. In Skylab, it was much easier to appreciate the meaning of the basic principles which we now call Newton's laws.
My first law states that a body remains at rest or moves with constant velocity unless acted upon by a net external force. My second law states that the acceleration of a body is proportional to the net force exerted on it.
found it quite easy to move equipment which would have been far too heavy for one man to handle on the ground. This gave us a real feeling for the way in which inertial mass resists the application of force. Inertial mass is the constant of proportionality in Newton's second law.
My third law states, when a body exerts a force on a second body, an equal and opposite force is exerted by the second body on the first.
Here Alan Bean is exerting a force on the walls of Skylab, which produces a noticeable shaking of the image through one of our solar telescopes. The wall exerts an equal and opposite force on him. Small thrusters in this astronaut maneuvering unit exert forces on the gas particles which they expel. The motion of the unit results from the equal and opposite forces exerted by the gas particles on the thrusters. In the zero-gravity environment, we could demonstrate many phenomena impossible to see on Earth, some with important practical applications, such as growing semiconductor crystals. The effects you see here are strongly influenced by surface tension forces. On Earth, these forces are overpowered by gravity. But the most remarkable effect in zero-G is the freedom of body motion in all three dimensions. Actually, everything we were doing in Skylab was an experiment in physics, and it was also a real opportunity for wonder and fascination.